Okay, welcome back. What we just got done doing is this construction to make parallel lines. And eventually what we're going to do is prove it. But I'd like to just jot down a few things. One, when I rotate 180 degrees. And I start with a point and the line itself, and I rotate this as my center, and I go 180 degrees. By now in geometry, what we should recognize is that the lines that we create have 180 degrees. And so by rotating, what I've done is I've created a line, and that becomes really important in our understandings. The other thing to recognize is if the point of rotation is not on my line, okay, lines preserve lines, and so when I rotate it around 180 degrees, you can see how this maintained its line, and I ended up with a parallel line here, and we're going to prove that in a second. The last thing that I need to make sure we really understand is that this is rigid motion. And what that really ultimately means is that when I move an angle, so if I look at the angle here at B and I rotate that angle around, it should maintain its measure over there at B's image. And so all these facts come together and they create the theorems that we've worked with parallel lines. Okay, so let me help you fill this in. It says, how does your construction relate to the geometry? In the above rotations, the proof will follow on the page. Complete the statement below to clarify your observations. And so a lot of us, in honesty, really on the quiz, had forgotten the notation. The capital R meaning rotation, the C or the point next to it is the degrees that I'm going to rotate. So this symbol is 180 degree rotation around C. Rotations preserve lines, and therefore the rotation centered at C of 180 degree maps the line L to the line L prime, which is the image. So what is the rotation centered at C of 180 degrees of point A? You might want to go back to this and essentially kind of play around with where things ended up. But if I rotated A, kind of look where A goes, well, A is now in the position that used to be occupied by P. And so as we spin this back around, the rotation centered at C of 180 degrees will be point P. Okay. Now you might be wondering what's going on with this. How do you know that they're parallel? Well, here comes the proof, and this is an awesome method of proof. So we've got deductive proof, we've got inductive proof, but we also have proof by contradiction. And what proof by contradiction is you take a statement such as, I want to claim that line L is parallel to line L prime, its image. The problem is that I'm not able to really state that through the means that I have presently. And so proof by contradiction first assumes the opposite of what you want to prove. And eventually, you'll follow a progression of things, and eventually you'll end up with a contradiction. Eventually end up with a contradiction. Okay, or two statements that oppose each other. And so the proof, we will show that assuming they are not parallel leads to a contradiction. Okay, and so if I'm looking at this first line, they say if they are not parallel, and they're talking about lines L and L prime, then they must intersect somewhere. Call it point X. And so I'm just going to use this space to draw a little bit of an image, but essentially what they're saying is you start with line L, you rotate it around a point, and the question is, are they parallel? Well, if I assume that they're not parallel, then they must intersect somewhere, and they're calling this intersection X. Since X is on line L prime, or the image of line L, there must be a pre-image that mapped to X. So since I'm on line L, which is the image line, there must be some pre-image, and we'll call this point S. Since the rotation of 180 degrees, and you kind of saw this with your circle, that means that these must be the endpoints of a circle. So I kind of should have some center point and be able to rotate around it, and it must be somewhere in between the two. So S and X must be the endpoints of a diameter of the circle that has center C. In particular, the line SX must contain C, and you can see that on this image. Since S is a point on line L, and X is a different point on line L, because remember, we assumed that they intersected, and we claimed that this was the intersection point of the two. We have that line L is equivalent to the line SX, because there is only one line through 2 points. But the line SX contains C, which means the line L contains C. But if you remember our beginning construction, right, C was the midpoint of P, so C was really originally that rotational point off the line. And it was that P to A deal where we were the midpoint, and the midpoint was C, that even allowed us to construct it. But C was not constructed so that it was on line L. So this right here, however, C was constructed so that it was not on line L, is that spot. And so the word "this is absurd," basically this is your contradiction. So there are only two possibilities for any two distinct lines, L and L's image, in a plane. Either the lines are parallel or they are not parallel. And since assuming that the lines were not parallel led us to a contradiction or a false conclusion, the only possibility left is that we get to state that L and L's image were parallel to begin with. So in other words, since we just proved that it's absurd or a contradiction that they intersected, and the only other option for them is to not intersect or be parallel, we now have two parallel lines, L and L's image. And so I'm going to pause the video. This was really deep, and then we'll continue on. So think about it. Try and make sense of this proof by contradiction. It's a really powerful method for proving something right or potentially wrong, and very useful in geometry this year.